So separate from thinking about what waves are, we have to now think about what waves do. Velocity, as we know, is represented in meters per second. And so we're going to be able to think about the rate at which waves travel, and we're still going to call that our velocity. So our velocity happens to be a product of our frequency and our wavelength. And so the answer there is sort of dictated in, well, the units. So what do we want? We want meters per second. And our hertz, the unit for frequency, is really a inverse second. It's the cycles per second. And so if we multiply that by our wavelength, a length in meters, we get a meter per second, which will describe the speed at which our wave travels. So next we kind of have to talk about, well, what happens when a wave reaches a boundary? A boundary here might just be my partner's hand in my spring lab that's holding the other end of the spring that I'm shaking. So if I think about this wave as moving to the right, there's a pulse, and the different pieces of this wave are coming to the right in that order. But what we see when this end is fixed, if we have a fixed end here, we're going to see a reflection. And so when it reflects, I see the opposite of what I saw. But I also have to think about that it's turning around and going the other way. So if it's turning around and now going this way, the first pulse is in front and it's on the bottom. The second part of that wave is on the top, and the third part of that wave is again on the bottom, and it's headed back where it came from. If the end is free to move, which was a lot harder to duplicate in our experiment, that wave is going to come in and it's going to turn around again, but this time it's going to not reflect because there isn't that hard boundary for it to reflect on. So if I go ahead and label them again, 1, 2, and 3, I will see the exact same wave, but my free end is going to cause no reflection, but the wave still turns around. And when it turns around, the velocity changes so that 1 is now on the left, and the second half and the third piece are behind it, but our amplitude has not flipped. It has not reflected. Another behavior we see with waves and pulses is this idea of superposition, and we're often going to see that with reference to interference. So what is interference? It's basically like overlap. And so if I have two pulses that are headed towards each other in different situations, on the top of this, you see that I have one with an amplitude, we'll call it 2, and the other one we'll call it 1. And so when they're headed towards each other with amplitudes on similar sides, I actually see that those are going to add together, and I get an amplitude of 3. And so we call this constructive interference because they are sort of having good overlap. There is similar amplitude. But conversely, if I have an amplitude of 2 and an amplitude of 1, or it's sort of going to behave like -1, I'm going to see a subtraction. And so I have a shallow pulse that when they're overlapping, they will subtract, if you will, and we call this destructive interference because they are opposite amplitudes that are going to subtract from each other because they have pulses on different sides of the wave, basically. So superposition is often just what we call like the combination, but we see it when we're addressing interference. And it's sort of that number, if you will, of when they're overlapped. And that can happen in simple or complicated ways. So you have to sort of apply this idea to different situations. So a special type of interference is called a standing wave. And so if we have this wave in front of us, but we think about this wave maybe reflecting off a boundary and then interfering back on itself, we have a wave that sort of just comes back into itself, and we'll often see it drawn like this. And so what that leaves us with is parts on this wave that appear to be stationary. In the center, they don't really move much, and we call those nodes. They are nodes, they're rigid, sort of like lymph nodes, or sort of like central locations in the lymphatic system. And then we have opposite that, we have these antinodes. And the antinodes are sort of the extreme opposite of the nodes, because what we have really is like a full oscillation from side to side, where these red nodes aren't really moving because we're sort of in rhythm with the wave. And we call it a standing wave. So how does this happen? Well, the nodes are maximum destructive interference. So I have complete cancellation. And what's happening at the antinodes is that I have maximum constructive interference. And that allows us to have these highs and lows that stay in the same place and just sort of oscillate back and forth, kind of like when we did simple harmonic motion, but in different chunks on our wave or on our standing wave. The last general wave behavior we're going to look at is called diffraction. So diffraction is more simply put as like a bending effect that waves have when they reach obstacles. Often we look at like openings, but it could also be like the opposite of an opening, as a sort of obstacle that a wave would move around. But here we're going to think about openings that waves are going to go through. So we have similar size openings across the top, and we have different size openings across the bottom, but then left to right, different wavelengths of waves are represented. And so those waves will bend given the opening that they're approaching, and the wavelength's going to stay the same. So if we see the similar wavelength, but bending as it gets to that opening, like that is our diffraction pattern. We see diffraction in the form of the bending of the wave. But when we have a bigger wavelength, those waves have to stay spaced apart. And so with the bigger wavelength and the smaller opening, we see even more bending, and we say there's even more diffraction. That pattern holds true, but also if I have a larger opening, well then the waves are going to form equally spaced apart with their wavelength, but they don't have to bend as much to sort of get through the wide opening because that opening is bigger. So I'll still see more diffraction with the larger wavelength, but as I compare the similar wavelengths to different openings, I will see that I have this less bend with the wider opening because it will have less diffraction as we slowly get towards, if that widened enough, there would be no thing to move through and there would be no bending because it would just continue to move like the wave was moving before. So this diffraction is bending, and we see it through or around obstacles.